Thank you. Oh, thank you everyone for coming along today, and thank you to the organisers for the chance to present at this amazing event. So in my 12 minutes, I want to build on some of the things that were talked on by Jermaine and also just give you my own take on this question about can a graviton be detected, and fundamentally what would that tell us about the quantization of gravity. Of course, even with the discussions, I won't be able to get through all of this, so please feel free to ask me some more afterwards, or also have a look at this paper that I wrote on the topic with Valerie, one of the organisers, and also Dan Carney. So because it's a short talk, let me just tell you essentially what is going to be the outline or the takeaways from the talk today. And actually, despite what I showed you on the title slide, I'm actually going to spend most of my time talking about something else. And that is because I've got 12 minutes, so I want to use them all. So what I want to focus on is this idea of a wave-particle boundary for gravity. Because actually this was the motivation for why I even started thinking about these questions to begin with. And I think independent of this question about can a graviton be detectable, this notion of a wave-particle boundary, at least for me, I think is a very useful way of internalizing this parameter space that we're all thinking about, the ultra-high frequency gravitational wave parameter space. From there, in my last few minutes, I'll touch these very small topics of is a graviton detectable and would graviton detection imply quantization. But just to tell you what my takeaway from these are, firstly, as we heard in Jermaine's talk, Dyson famously concluded no. I'm in full agreement with him that I actually do think it is possible. But then, depending on exactly what your threshold is for saying that you've discovered that something is behaving quantum mechanical, if you apply the threshold that is in quantum optics, for example, I would still say that this is no. But this is certainly something that's open for debate. So let me turn to this first picture of this idea that there's this threshold between where gravity behaves as a wave or a particle. And the way to see this is to look at this parameter space that you've already seen many times this week, and you'll see many more. This is the parameter space for ultra-high frequency gravitational waves, so looking, for example, purely above 10 kilohertz. So we all know this, but just let me remind you something important about what we're showing on the y-axis here, this strain value. So although this is the way that this is commonly parameterized, and it's a very useful way of thinking about what you need to achieve experimentally to make a detection, remember that another important parameter is the amount of energy density in this gravitational system, and that is controlled by the strain squared and the frequency squared. And so that means if you stay at a constant value of strain here, you are not remaining at a constant energy density. Contours of constant energy density move as 1 over frequencies. They'll be moving down this plot here, and that's an important point to keep in mind that I'm sure many of you are aware, but it still, I think, is worth repeating. So with that said, let me just give you a quick summary of the achievements of everybody in this room, and I'm surely missing many more. And that is that we can make enormous cuts into this parameter space with various ideas that are already in existence or we hope to have in our hands in the near future. And of course, I'm sure that at this point, what I'm showing you here is very much out of date. So there's a lot more subtleties to this, but the way I like to think about this parameter space is that broadly I can break these types of techniques into two sorts of experimental search systems. The first of these, on the left-hand side, is where I'm using the gravitational wave to induce, as sort of a coherent driving force, to induce a response in some harmonic oscillator system. This is usually how these systems are boiled down. It's certainly the one where I'm most familiar, where, for example, you draw analogies with the searches for wave dark matter, where the wave comes in and drives some resonant response, for example, I'm showing you an example here I'm particularly fond of. This is the abracadabra experiment. And there's broadly many experiments of this type. For example, even Weber bars can be thought of this, where the gravitational wave is driving some harmonic oscillator response in that mechanical system. So that's one class of experiments. But then if we move to higher frequencies, there's sort of a slightly change in thinking about the types of detectors we have. Here, instead of looking for some harmonic response, instead we're looking for individual states undergoing some conversion to an observable state. So for example, here we're looking for a graviton to be converted into a photon in instruments like CAST or ALPS that we heard a lot about yesterday, for instance. So despite all of these achievements, the other thing we've already heard about is that we want to do even better because the ultimate goal of this is to get down to the real promised land where we could see unique signatures such as high temperature phase transitions or the athermal graviton emission from the primordial plasma. But of course the challenge here is keeping in mind that this means that we have to get below essentially the energy density of the CMB, and again this runs as roughly 1 over f in this plot here. So this is just recapping things that I think you're all probably familiar with. What I want to add to this picture is one additional line. And that is this boundary between waves and particles. Now, I'm sure many of you have thought about this before, but if you haven't, the analogy that I'll bring to your mind is the one that we have, for example, in the dark matter community. There, fundamentally, for a long time, we've been looking for dark matter as a WIMP, which is a GeV scale particle, and we think of it as just some gas of particles around us that could be bumping into our detector. On the other hand, if we go to much lighter dark matter, we start to think about this as behaving as some coherent wave, and instead we need to come up with completely different search strategies to look for it. But this is a transition that any bosonic energy density can undergo. Of course, the electromagnetic spectrum famously goes through it as we go from gamma rays to radio waves. So you'd ask the question, where in the gravitational parameter space would this same transition occur? And I can tell you it would cut right through the parameter space that we usually draw here. In fact, I mean, you can go through a more sophisticated version of this calculation, but fundamentally what you want to determine is when do you have the states not overlapping, or essentially where is the boundary where you have one state per its own inherent volume. So its own inherent volume is defined by the fundamental size of it, for example, the de Broglie volume. And one way you can compute where this boundary line is you just take the number density of gravitons you have and multiply it by the de Broglie volume. You can rearrange this, of course. We can rewrite the number density as the energy density over the energy, and then the de Broglie volume dropping factors of 2 pi. I can just write that as 1 over the angular frequency cubed. And then using the fact that the energy density is the strain squared, the frequency squared, and Planck squared, I get this expression that I'm showing you here. And then it's easy to substitute numbers in and find out that this is roughly where this boundary is. So this tells me that if I'm well to the left of this line here, I really can think about gravity as acting like a classical wave, just in the way that we think of axion dark matter as doing this. Whereas if I'm to the right, I should think about this as really acting like a gas of gravitons. And if nothing else, this gives me some intuition for the types of detectors I'd want to build for this, and loosely why we saw this separation between the two types of instruments I mentioned at the outset. But now finally coming to the main part of the talk, what I want to emphasize is that if you want to make a detection down in this purple region here, what this insight tells you is you need to detect a single graviton. That is what the detection is going to amount to. And then if you'd read Dyson's paper, like I had when I first drew this line, you instantly think, well, maybe this is a completely no-go region for the detection in this field, which, I mean, we already know it's hard. This would be extremely pessimistic if this was the takeaway from this statement. So there's quite a lot in Dyson's paper. It was actually the last one he wrote, so I encourage you to have a read. But just one other point to emphasize that Jermaine didn't touch on. I think my favorite argument of Dyson's in that paper is he takes the idea of a LIGO-type interferometer, and he said, what would it take to get an instrument like that down to the sensitivity of strains of about 10 to the minus 40, which is what LIGO would need to achieve to hit this threshold here. And he concludes that such an instrument would almost irreducibly collapse into a black hole, which suggests that making a detection here could be inconsistent with the fundamental laws of physics. And if you take that seriously, you might think that, well, okay, if I extend that, this whole region may be inaccessible. But the reason I don't think that's the case is that as we move to higher frequencies, a detection actually becomes considerably simpler for two reasons. The first of these is you can see the way this line is operating, it's moving to higher strains. So if we move well above the LIGO frequency, experimentally it's going to be easier to detect. And secondly, if you recall that on this plot, lines of constant energy density are running away from us, a signal at that sensitivity threshold has a much, much, much larger energy density than one down here. The sources themselves are going to be more intrinsically detectable. So if you think differently, it might be possible to come up with an instrument that not only could make a detection, but at the same time wouldn't collapse into a black hole, which is a very desirable property. So just to roughly run you through this to convince you that it is in fact possible to make a detection here. As I told you earlier, this boundary is set where the strain is roughly the frequency over m Planck. So let's focus on cast, which is already claimed to get sensitivity into this threshold here. And at cast, it operates at roughly a keV, and so a keV over the Planck scale is 10 to the 3 over 10 to the 27 eV, and so it's 10 to the minus 24. So I've roughly drawn it in the right place here. So let's stare at this cast sensitivity threshold and just check, does anything crazy happen if I try and make a detection at this threshold? Something crazy is happening, but I'll come back to that in a moment, but it's certainly not that the instrument's about to disappear inside its event horizon. So the point I want to estimate is for a source sitting here, what would I see at cast in terms of the number of signal events per year? And as I'm sure some of you are aware, by the end of its operation, CAST was such a phenomenal instrument that it was seeing very few background events per year. So if I can get an order 1 number of signal events, in principle, this could be a detectable signal and would confirm that such sensitivity thresholds are achievable. So in order to compute this, I just want to determine what is the incident number of gravitons, and then what is the probability that those gravitons became a photon that is the signal in my instrument. Good, so for that calculation, I can just take the number density times the incident area of my cast telescope, for example, and the collection time, and then again I need to multiply it by the conversion probability. I can rewrite these. The conversion probability famously is given by this combination of expression terms here, and I can rewrite again the number density in terms of the energy density over the energy, use this same expression in terms of M Planck, etc. I get this combination of factors here, where I've written the area of the bore of cast as some experimental length scale squared. Interestingly, when I expand these two out, I find that the Planck scale cancels. This is sort of an idiosyncrasy of describing this in terms of the strain. But when I get all of these factors and put in roughly values that are experimentally achievable or not too far away from what cast has, you can see that at about 10 to the minus 28 in strain, you would get about 10 signal events per year. So not a lot, but this is a number that is greater than 1, and you could imagine actually detecting this. So it seems not insane that cast could have made a detection here. Up to one caveat, that such a source at that level is a little bit insane. And then the reason for this is that I'm imagining some source of keV gravitons that persists for 1 year. So I have no such source in mind that could actually generate this. However, Dyson was making the argument about the ultimate form of an interferometer you could build. With all due respect to the cast collaboration, it was a wonderful experiment, but I don't think you would classify it as the best possible experiment we could build within the laws of physics. So you could imagine building an even better version of cast, and with that in mind, it would in principle be possible, I think, very much to detect a graviton, I think in exact agreement with what Germain said. So in my last 30 seconds or so, let me explain, though, why I don't fully agree, at least by some standards, with what Germain concluded, in terms of if you actually made this detection, what would you then eventually conclude about the quantum nature of gravity? So just to say, I think actually it's also fair to mention that why Dyson was asking this question originally was exactly by the analogy to the photoelectric effect. Of course, in the history of science, the photoelectric effect is what eventually led us down this path of quantum mechanics through Einstein's insight. And so Dyson said by analogy, and as expanded upon by Germain, this would then also tell us that gravity itself was quantized. However, in quantum optics, it's since been realized through not necessarily completely technical arguments, but essentially if you have a classical source that is incident upon the metal that Germain was describing, you can also emit electrons with all of those three core predictions that Germain explained. Of course, as Germain went through, when you start to think about how these models actually operate, problems begin to emerge. So one thing you might have to stomach is that your model of the universe doesn't satisfy energy conservation. That is not always what is done in the literature, but that is one possibility. Another possibility is that instead of quantum mechanics being fundamentally linear, you would have to give rise to some theory of nonlinear quantum mechanics, for example. But if you're willing to stomach one of those possibilities, it is still allowed that a classical interaction could reproduce all of the effects of the photoelectric effect. And so then you can ask, but is there any experimental measurement I could do that could even rule out those systems? And indeed there are, they're just extremely hard. For example, in the case of one of these, famously the sub-Poisson measurement, what you need to do to achieve this is you need an extremely high efficiency detector. This means you need your P, the probability of a graviton converting to a photon, to be roughly order 1. I can tell you for cast it's about 10 to the minus 33, so you're many orders of magnitude away from that. And secondly, you would need a fundamentally quantum state of your incident gravitons. For example, you'd need it to be a squeeze state, which there may be some ways of producing, but this is also an extremely hard possibility. So taken together, I think actually achieving what is the quantum optics gold standard in this sense for these measurements doesn't seem like it's about to happen anytime soon. And actually one other thing is, despite Dyson's fascination with it and my own fascination with it, this measurement has nothing to do with this wave-particle boundary that I showed you earlier on. Whether you're making a measurement above or below the line, that doesn't tell you anything about whether this thing is quantized. You really need to do something else, like by one argument, the very precise measurements that Germain described, or by another argument, these types of extremely hard measurements to see sub-Poisson statistics. Okay, so that's the main takeaway from my talk. I think that this wave-particle boundary is a very interesting way of internalizing some aspects of this high-frequency gravitational wave parameter space that we've all been interested in. However, unfortunately, I don't think this line has anything to do with determining the quantum nature of gravity. Okay, thank you.
Okay, thank you very much. So are there questions for Nick? So, okay, go through it. Let's start there and go to the right.
Okay. Well, very interesting talk. Thank you. So, for instance, what will this line will teach us? For instance, we have this for looking for detections for, say, phase transitions that fit into those two sides. So what will be make a difference in search for gravitational waves from on the each of the two sides for phase transitions?
So there are many lines on this wall, so I assume you're talking about the purple line.
Purple line,
yeah,
yes.
Exactly. So for me, I think of it, so actually my background is in dark matter searches, and so this is why I was motivated to draw this line, because I'm thinking about this all the time. I think it helps internalize what type of detectors might be useful to get to what parts of the parameter space. Just in the same way that you're not going to build an enormous vat of xenon to look for axions necessarily, right, for instance, because there you're looking for some discrete scattering event. And here we're looking for some discrete conversion event, for instance, whereas on the left-hand side you're looking for some coherent wave possibility. So pushing those instruments up will work to a degree, but maybe as you move all the way down you need to think of something different. However, this is just a qualitative distinction. There's no sharp transition that occurs at this line. And indeed, these cases are always mixed. I think actually Jermaine's talk was a very nice example of this. I would normally think of a Weber bar as a mechanical harmonic oscillator system. But of course, as you really drill into it, it's fundamentally quantum mechanical with energy levels, and you can even realize some of these particle aspects at that level as well. So for me, honestly, I think that this line gives me the same qualitative insight as I get for dark matter, but I wouldn't take it too literally in terms of exactly what's happening right at the line and these other questions, for instance.
Okay, thank you.
Thanks for the question.
Juan?
So you were mentioning squeeze states as a characterization of quantum gravity, but we know during inflation we do excite modes, high occupation numbers.
Yep.
We call them tensor modes, just gravitational waves, but they are really quantum modes, highly excited though. So would you be able to look into coherence properties of those waves in order to find their quantum nature?
Great
How would
question.
you do that?
No, great question. Yeah, so as I haven't gone through this in detail, but these, I mentioned one of these possibilities is something called sub-Poisson counting statistics. This is where you're just counting the number of events that come in, and you see that the variance in that is less than the Poisson distribution. And the way that can occur, one way you can imagine it, is if my incident beam is really made of quanta, I can up to, roughly send them in one second at a time. And so if I ask how many quanta do I get per second, and if I have a 100% efficient detector, I'll get one with zero variance. And you can show that a squeeze state can actually reproduce this. But it turns out for this, for that argument to work, you needed the high efficiency detector and you needed the quantum source. So one of the only ways that I've seen put forward in the literature to actually generate a true quantum source of gravity is inflation, because of the fact that it can squeeze this. However, the other thing that I would say about that is another version of the sub-Poisson measurement is you can also look to measure quadratures like the field value or a magnetic field or electric field. And actually, where the quantum information is hiding is if you can see that the gravity interacting with your system can move one of the quadratures to be less than the fundamental half that is required by the uncertainty principle. So the problem is with the squeezing, you actually have to see the small state. That's where the quantum mechanical information is hiding by this definition of what quantum mechanics requires.
I guess you won't be able to see that in the polarization of the CMB, right?
Yeah, this is the usual conclusion. So the problem is the thing that is squeezed to the large value is the one that is not holding the quantum mechanical information.
So I have an alternative thing, which I already proposed, which is if you have fluctuations in the scalar part, not in the tensor part, from inflation, those fluctuations eventually collapse to form black holes. They would be primordial black holes at causally disconnected regions of the universe. They might be entangled. If the number of efforts that happened between the time they formed, the fluctuations that left the horizon at the end of inflation is not too big, the squeezing state is not very highly squeezed. And there you could try to look for these entanglement entropies between those black holes.
That's very interesting. Maybe just one thing to say beyond this. The other gold standard that quantum optics has allowed is entanglement. So if you show that something, for example, violates some Bell's inequality, which potentially you could see some evidence in the structure that your system had entanglement there originally, that would also prove that that the source that generated it was fundamentally quantum mechanical. Very small scale. I'm not saying, of course these things aren't. I mean, but it could be much easier than having an order 1 efficient graviton detector. Yeah.
There was a question here and another one.
Yeah, so just to understand this slide, you say that a proof of the quantum nature of the gravity would be to have a very large probability of conversion, and that conversion to be in a squeeze state. What if I consider the opposite situation, where I have a source of light which is squeezed, and I convert it into graviton, then I detect that graviton? Would that confirm that is a quantum gravity?
So I generally, I mean, you would think that this will carry some of the information through into the graviton source, I guess is what you're trying to suggest here.
Yeah.
The challenge with this is, so often what, maybe paradoxically, in a lot of these arguments, where the proof of quantum mechanics is made is in seeing extremely small variance. Like what you really want to see is that this thing is made of quanta, and quanta can have smaller variance than any classical wave can produce. And so the problem is, if any part of your system introduces variance back into the problem, you wash that out. So a low efficiency detector washes that out. And I worry in the example that you're putting forward here, unless you have an extremely high probability that the graviton becomes a photon, even though there's some quantum characteristic in your input source, it will be completely washed out by the randomness of how many of those states actually get converted into the gravitons that you're looking at on the other side.
Yeah, thank you.
Okay, Camilo?
Thank you very much, Nick. It was very interesting. So how much of your arguments depend on the graviton being strictly massless? So in other words, if you have a slightly massive graviton, what would happen?
Well, yeah, so I mean, there's problem enough with these arguments. Trying to determine whether massive gravity is a sensible theory to consider also is another challenge. But I think fundamentally, no aspect of the arguments I'm putting forward require this to be massless. I really think like determining whether a bosonic system is made up of quanta, you could go through the same sort of arguments. I don't see, like all of these arguments were generated for light, but I don't see this as, you could use the same set of arguments, like let's say, as I'm hoping in the next few years we detect dark matter, if you then wanted to say, can I prove that dark matter is fundamentally quantum mechanical, and of course we know it has to be massive, it will be similar sorts of arguments that you would need to put forward in order to prove it to the gold standard of quantum optics, which again, I mean, there are different ways of arguing what is a necessary condition to prove something's quantum.
Okay, thanks.
No, thanks for the question.
Okay. Yeah, maybe as a brief reminder, I see you. This is now transitioning into the general discussion session. So, of course, if you want to ask questions also to the previous talks, you're encouraged to do so. But I think we have another question in the back, so please go ahead.
Yeah, so I really like the purple line. I wonder if I can make a request to add another line on that plot. Where would the single graviton line, like how below the purple line is that single graviton line?
What? Oh, good. To clarify, this in some senses is the single graviton line. So this is the line where, if you think about, every photon or every graviton will have some characteristic size described by its de Broglie wavelength, or equivalent because it's massless, it's Compton wavelength. At this boundary, for that energy density, they're all just sitting packet to packet next to each other.
Well, I guess what I mean is, so if I think of an electromagnetic wave, I can say the amplitude of the electric field, I can like sort of relate that to the number of photons in the laser.
Yeah.
So the amplitude is h here, right? So does this amplitude at this line correspond to one graviton? I'm guessing no.
I guess one other thing about this, of course, it depends. If I want to think about, you want to think about the one graviton Fock state, for example. And in that sense, I need to start specifying experimental parameters, like what is the size of my system, because then for a given energy density, I know what is the number density in there. I can figure out what is the actual number of states I have associated with that.
I guess
So
maybe I would just use the coherent state, right? So if you have a coherent state, you have an alpha, and alpha could get related to h, and alpha is related to the number of photons. So perhaps that would be like a use, and intuitively I would imagine that line would be much, much below the purple line, but parallel to the purple line.
If you used a coherent state to do this calculation, the point where the magnitude of the coherent state is equal to 1 is this purple line. So in that sense.
What would it mean for some experiment to detect below this purple line that they're detecting a part of a graviton or something?
No, oh, good. No, I mean, you can. The gravitons are now just further apart. So this is the exact same transition between radio and gamma rays. Like gamma rays aren't, the wave packets aren't just sitting right on top of each other, they're extremely far apart. These states are very dilute. And you can think of them as coming into your instrument one at a time. And it would be exactly the same way for the gravitons in this regime here. It's just a dilute gas of particles flying around.
Perhaps the confusion is about 1 graviton per watt. I think if we want to draw a single graviton line, we have to specify 1 graviton per watt volume or watt time interval and so on.
And here, the volume I'm defining is their own intrinsic volume, but that changes as a function of frequency, of course. It gets smaller as you move to higher frequencies. Yeah. Yeah, but for a given experimental size, I can go through this exact calculation you mentioned. Yeah.
Okay. Yes. Once more, this row here.
It's a side issue, but would you then claim that detecting gravitational waves from inflation would be approaching quantum gravity? Because that has been a discussion for quite some time, and there are many different approaches to it.
No, I mean, and this is where also I would be interested in the thoughts of Germain as well. I mean, these questions of what does it take to prove that something is quantum mechanical? People go back and forth on in the literature a lot. And again, I didn't say too much about this, but we maybe can say some more. The theories where you continue to treat the incident thing as classical, but everything else is quantum mechanical, are deeply perverse. I think most of us, well, I don't want to speak for everyone in the audience, but I think we all probably hope that's not the fundamental theory of the universe, where you invoke something like nonlinear quantum mechanics, or you have to give up energy conservation, for example, in the way that Germain put forward. But why these arguments, I think, at some level have become so popular in quantum optics, I mean, I think Germain would say it's because they can be done experimentally, so that's a reason why the quantum optics people like them. Another reason is that for many of the cases that people put forward of these alternative theories, you can just prove that there's none of these classical models could satisfy these experimental observations. That doesn't mean there's no loopholes. I think like some non-local theories can still get around some of these examples. Germain may know others. But in that sense, like these sorts of arguments, I would take this as very suggestive that you were seeing some quantum mechanical effect. But would you convince the entire community that you've proved gravity is quantized? I will tell you now, you will not.
It's more like quantum field theory in curved backgrounds rather than quantum gravity, no?
But if you know, yeah, I mean, but as soon as you start putting, if you just take the Newtonian potential, and as soon as you say that you want that to have come from some theory that was unitary, you can essentially derive the existence of the graviton. And then the question is that we probably all think that's the way it goes, but if it's not quantum mechanical, maybe it doesn't have to be unitary. These sorts of statements come up.
So I lost track a little bit. Valerie, you had a comment on this? Or?
Well, I just want to comment directly on that, so maybe I can jump the line. Yeah, because we've been discussing this also a lot, right, with the CMB. So I think if you just measured gravitational waves with a wavelength matching a CMB, right? Then, as a cosmologist, you will probably already be convinced, right? Others probably not yet. But then, for the CMB, the nice thing is we also have other predictions, right? I mean, we would kind of see the correlation between the tensor modes and the E modes and the T modes and the cross correlations, right? And we'd see the super horizon. And despite it wouldn't be a complete formal proof that you cannot come up with some completely absurd model which might try and generate that, I think.
That would be quantum field theory in curved space.
No, a classical model.
What do you mean? Fully classical?
A fully classical but completely pathological model, right? Mm-hmm. You can maybe construct, right? But at some level, you and I and most of the community would just see, okay, well, but the logical explanation is inflation, right? So there's, I think, a bit of a point kind of in the special case of inflation, because it's not just that you see a single click somewhere, but you have so much information. At some point, you would just be convinced, even if it's not a rigorous mathematical proof, right? Here, with these arguments, right, about the Poisson statistic, one is really aiming at rigorous mathematical proof in a lab-based experiment. So the bar is a bit different.
Okay, yeah, there's a question in the back.
Well, Germain also, I think, wanted to weigh in on this.
Okay, and then you. Okay.
Yeah, it was more just a question for you specifically.
Sit a bit closer to your mouth.
So, am I answering the question or Germain?
Oh, sorry, the other Toba.
I'll go after you.
Yeah. So, what? I mean, what? Do you still think that the single graviton clicks provide some evidence for the quantization of gravity, or would you say you have to have that gold standard of quantum?
No, I'm putting it right to the point. I honestly don't think I have a complete answer for myself yet. Yeah. So I think that being completely frank, I've come into this literature about a year ago, having mostly thought about dark matter, and mostly when you read about the quantum optics, they're very obsessed with this gold standards that I've run through here. But a fair standard is, I mean, they are focused on a field where we can perform all of these measurements, and I maybe didn't go through the specifics, but what you would actually require to do to prove one of these subquantum statistics, I don't think is really achievable in our universe with the laws of physics that we have, other than the entanglement route. That may very well be achievable. And if you can't reach this standard of the quantum optics is set, then I think it's absolutely critical you go back and think how much have we learned from all of these steps. But I would say at this stage, I've actually in the last few days, just in discussions with yourself, been actively learning about how much we're learning from this. And so I think that you do learn something non-trivial from what you're seeing in these measurements, but I still have to digest that some more. So let me hedge my answer as thus. Yeah.
Okay, thanks for the really interesting talk. Just last week, I saw this talk, which also gave a gravitational photoelectric effect by Giovanni Tomaselli, and he was talking about a gravitational atom, what I could see from there is that when we look at photon-matter interactions, which the photoelectric effect is a matter-photon interaction, we're tied in with the quantization of charge. In your calculation, you had the Planck mass, but there's nothing special about the Planck mass. It's
cancelled out in one part.
Yeah, that's why it cancelled. I was expecting that. The Planck mass is not special. It's just a mass of some equivalent mass of some energy scale. I can't see anything special about it.
Just to say one
what
thing.
We really need is the minimum mass. What is mass quantized? And then we could have, in this model that I'm talking about, I don't know if you know of this work about the gravitational atom. He gives a gravitational equivalent to the fine structure constant, but where it falls down is he doesn't have a quantized mass like you do a quantized charge in that interaction. So
just to say a few tongue-in-cheek, I was being tongue-in-cheek about the cancellation of M Planck there, just to emphasize in case it wasn't clear. I mean, what didn't cancel out was H. And the reason why the strain is so small is because M Planck is so big. So, I mean, M Planck hasn't completely cancelled in full spirit there, right?
Well, H is something else. That's angular momentum.
No, H is, I'm talking about the gravitational wave strain is what I meant here. So if M Planck was much smaller, the strain would have been much larger. So it's actually, you can't completely disentangle. It's just a feature of how I've written it that way. But to say, like, in this picture of, I mean, just to clarify in what I'm talking about here, there absolutely is something quantized, and this is the energy density. In this picture here, it's been quantized into little packets. I mean, that's the fundamental thing that you're looking for. I don't need some other...
okay, so what about this concept of a gravitational atom, like around a black hole with energy levels?
Well, in that case, I mean, I know a little bit about that work, but not a lot. But essentially, it's just a gravitational analog of the hydrogen atom. And one of the distinct things that, I mean, even Jermaine mentioned in his talk, that you can see these transitions between the levels there. And if one of those transitions is gravitationally induced, I would think that would be very strong proof of the quantum nature of that effect. Just as seeing some transitions between these effects in the hydrogen atom would tell you a similar thing about...
but I don't think the gravitational atom is quantized.
There are quantum energy levels in that system. Yeah,
but I mean, so the hydrogen atom doesn't prove that... does it prove that electromagnetism is quantized?
No, it proves that that state... it proves that the particles that made that up are quantized, like the electrons and the protons, for instance.
So then the transitions in the hydrogen atom works exactly the same ways in the photoelectric effect. So it provides evidence to the same extent as the...
Yeah, but the fact that there were energy levels in the first place showed you that something was quantized.
That's because we can have a fine structure constant. We don't have the equivalent in gravity.
There is such, I believe in that literature there is a way of forming it.
What mass do you put in there? There is no gravitational fine structure constant because we don't have a quantized mass like we have a quantized charge. And people will put Planck's mass or whatever mass, the Stoney mass or whatever, but it's not fundamental like the fine structure constant is in an interaction of electromagnetism with a quantized atom. So these, as far as I can see, these gravitational atoms are not really quantized. They're just, it's more like modes in a cavity based on the, which are...
Well, the modes in a cavity are quantized, right? So
Huh?
the modes in a cavity are quantized.
Yes, but it's nothing fundamental. You don't need quantum mechanics for that.
Sure, it's a wave effect.
Yeah, so I think that this is the same, and I think that this is a missing point in quantum gravity, that there's no quantized version, there's no quantized mass.
Are these new models from Magdalena on quantizing mass energy?
So what is the quantized?
So where you so one way of modeling quantized mass is say you have an atom and it could be a quantum clock. If you put it in a magnetic field, for example, it's processing, and that procession is an internal energy, and that could contribute to the mass by mass energy equivalence. So therefore, if you have a superposition of energy states by mass energy equivalence, you could have some concept of a superposition of mass, but it's coupling to the gravitational field would be quite weak.
Okay.
But anyway, let's talk about this more offline. There's a lot more I could say about that.
I think there was a question here or a comment on this.
No, just a comment. If space and time is quantized, would that lead to quantum gravity? But not saying anything about the mass itself, because the mass will quantize space and time. But indeed, the space and time can be quantized. We don't know what's the level of quantization.
At my very superficial picture, I would say yes, right? Like this way that I'm writing down the gravitational wave here, I'm now imagining that these perturbations of space-time are made up of little packets.
Yes.
Right? So that would be my way of thinking about it. I would think so from this, yes. But again, you need to often be very careful about this statement. So let me not say that that's 100% true, but that's what I would think, yes.
Okay. Thank you.
Okay, so I think that we are slowly approaching the end of this discussion session. So maybe a reminder, I think that now next is a coffee break, and then there is a scheduled discussion, not here, but in the seminar room. So next to the coffee room, the main topic will be the formulation of electromagnetism on curved spacetimes. And with that, I would like to ask you to thank again all the speakers, and Nick in particular now.